In this presentation, I'll be explaining sinusoidal pulse width modulated inverters, PWM inverters. Sinusoidal pulse width modulation, all that's called PWM. Instead of maintaining the width of all pulses the same as in the case of multiple pulse width square wave PWM modulation, the width of each pulse is varied in proportional to the amplitude of the sine wave evaluated at the center of the same pulse. Now, in multiple pulse square wave PWM modulation, we have noticed in another presentation that here the square wave is the modulating signal, and that is compared with a triangular carrier signal. And in that case, the pulse width of these multiple pulse widths were equal. But in this case, instead of the square wave modulating signal, we are using a sinusoidal signal as the reference or modulating signal. Now, the pulse width here, we can see that one, the pulse width will be varying one. Therefore, that pulse width will be proportional to the magnitude of the sine signal or sine of modulating signal at its center, that is this one. Therefore, here if you see that one, the pulse width is less because the magnitude of sine wave at this point is less, or that the pulse width is proportional to the width of each pulse is varied proportional to the amplitude of sine wave evaluated at the center of the same pulse. The center of the same pulse, what is the height? Now, let us see the working of the pulse width modulation, sine pulse width modulation, in which here, this is a circuit topology as such, same as we already seen in a single phase bridge inverter circuit, in which there are two legs. In each leg there are two switches. It is marked as here S1, S1, S2, S3, S4, and across each switch there are feedback diodes D1, then this is equal to D2 and D3 and D4. The load is connected between these center points, that is named as A and B, and a positive voltage we are taking this one as positive with respect to his, and similarly this is a positive current, and across this one a DC voltage is applied here. Therefore, this is a circuit topology, and in that one the controlling of the switch here as same as the multiple pulse square wave modulation here, same as this one. During the positive half cycle of the sine wave, that is during the positive of the sine wave, S1 is closed. S1 is closed. And when the modulating or reference signal, or it's also called modulating signal or control signal or reference signal, once that modulating signal magnitude is more than the carrier magnitude here, then S2 is closed. Therefore, here if you see that one, during this period, the modulating signal or sinusoidal modulating signal magnitude is more than this triangular carrier signal. During that period, S2 is closed. When S2 is closed, here plus voltage coming and here negative voltage coming. Here the same voltage as this one is coming at this point. Therefore, during this period, you are getting a plus voltage. And during this period, the modulating signal voltage is less than the carrier voltage, triangular voltage. In that case, the switch is turned and this is off. And during this period, again here, S1 is permanently on during the positive half cycle of the sinusoidal signal. Therefore, during this period, again we can see that the magnitude of the sinusoidal voltage is, or this one, that is low frequency sinusoidal voltage, which is the modulating signal, that magnitude is more than the carrier signal. Then S2 is again closed. Then that is here again, when S2 is closed, you will be getting a positive voltage here. And like same thing happens. If you look into that one, we can see that the width of the pulse is changing. That is proportional to the magnitude of the modulating signal, sinusoidal modulating signal, which is magnitude at the center of this pulse. Therefore, this is during the positive half cycle, and during the negative half cycle of the modulating signal, S3 is permanently on and S4 is controlled here. Therefore, when here again the same rule is there, when the reference signal or modulating signal magnitude is more than the carrier voltage here, then this is closed or S4 is closed. Therefore, during that period, when S4 is closed here, negative is coming here, and here S3 is closed plus, or you are getting a negative voltage. For a negative voltage is coming during this period. Again, during this period, since the reference voltage or modulating voltage is less than the carrier, magnitude is less than the carrier voltage, here that is open. So this switch is open. Therefore, you will be getting a 0 voltage. Again, during this period, the modulating signal voltage is more than the carrier voltage. Then again, S4 is closed. Then during that period, you will be getting again a negative voltage between A and B. A negative voltage is getting. So that pulse width is, varying proportional to the magnitude of the sine signal, which is the modulating signal. Therefore, you can see that one, unlike the square wave multiple pulse PWM, here the pulse width is changing and the width of the pulse is proportional to the magnitude of the sine wave. That's called Sine PWM. And the generation of the control signal is that circuit is already, we have seen that one. In that one, this is the same as the circuit topology, or this is the generation of the gating signal. This is the gating signal to the S2, which is the triangular signal is compared with the sinusoidal signal. And once the magnitude of sine wave signal is more than triangular signal, that corresponding switch is closed. In this case, S2 is closed during the positive half cycle, and in the negative half cycle, S4 is closed. Therefore, this is a control method, and thereby you will be getting the output voltage as output of the voltage. Across B, you will be getting a voltage like this one, whose pulse width is changing proportional to the magnitude of the modulating signal. Now coming to the working of a single phase half bridge inverter controlled by sinusoidal pulse width modulation, Sine PWM. So this is the circuit topology, and here the supply voltage is VD, and that is divided into VD by 2, VD by 2 by 2, same value of the capacitor. That is the center point. With respect to this one, will be plus VD, and with respect to this one, you'll be getting minus VD here. And this is the only one leg because it's a half bridge, and that inject this is equal to T plus and this is equal to T minus. Across each switch, controlling switch, there are feedback diodes, D plus and D minus. And here this point is named as A. Therefore, here the voltage of A with respect to this center point, VA0 is here. That is plotted here. Now let us see the working of that one. That is, this is the controlling, that is a carrier signal, is a called triangular signal. That's a carrier wave signal, VTRI, or that is the carrier signal. And this is the modulating signal. That is a low frequency sinusoidal voltage is the modulating signal, or sometimes we call it as reference signal or control signal, like that. Therefore, this is the carrier signal is modulating signal magnitude is compared with the carrier signal. And as per this control law, that is, if control voltage is same as the modulating signal. If control voltage is more than the triangular signal VTR, then here T1 is on. T1 is on. That is, here if you see that during this period, control voltage is more than the TR, then T1 is on. T plus is on. T plus is on. T plus is on means this is on. Therefore, here the voltage will become, that is VA with respect to 0. That is VA0 will become equal to, it is equal to VD by 2 plus VD by 2. Similarly, second, if this the V control voltage is less than the triangular voltage, that is during this period, you can see that one. Here T minus is on. That is T minus is on. As the T minus is on, here minus terminal comes VA, and with respect to that one, we'll be getting a minus VD by 2. Here, therefore, during that period, you'll be getting a minus VD by 2. Therefore, this is the control law. Based on that one, if you are comparing with a modulating signal of or reference signal or control volt signal of the sinusoidal with respect to a triangular carrier signal, then as per this control law, we'll be getting the output voltage of A with respect to 0 point like this one. Therefore, you can see that one, the pulse width is here. Here plus and minus are equal. The gain plus is increasing, minus is reducing. Therefore, that is maximum plus, that is that duration, that width is maximum here. Again, that is reducing, and here again plus and minus will become equal. Then again minus side is increasing compared to the plus side, and that is minus side is maximum. Again it is coming back, plus and minus equal, almost equal. In that case, actually this is the output voltage of the A and 0, between A and 0. And if you take the fundamental of that one, that signal will be in phase to the modulating signal. This is a fundamental one which is in phase to the modulating signal. And the magnitude of this one, the magnitude of this fundamental, maximum magnitude of this fundamental is given by MA into, we'll see that one equation will be in the next slide. It is equal to MA into VD by 2. That is the maximum magnitude. Of course, RMS value equal to divide by root 2 of that one. Therefore, in this case, here, if you, this is actually the the fundamental voltage of this one. If you do the Fourier analysis of this one, the fundamental component is this one, which is in phase to the modulating signal. just to actually this fundamental component is actually you can get by integrating this one. By if you integrate this output voltage of this inverter, you'll be getting the fundamental. As we have seen, just to explain that one, see this positive area equal to negative area. If you add that one, net area equal to 0. If you integrate that one, that is why you're starting from 0. Then again, if you looking going further, positive areas more and negative areas less. Therefore, net area will become positive. Therefore, that is linearly increasing and that reaches to maximum. Maximum positive area comes here and again that is reducing. And in this case here, negative area is more than positive area. Therefore, that's a principle of integration. Therefore, it is actually integration of this square wave that is called the fundamental voltage of this inverter, and that is will be in phase to the modulating signal. And there are two terms to be explained. One we call it as amplitude modulation, MA, amplitude modulation index, MA, which is the ratio of the maximum value of this control voltage or maximum value of this modulating signal, that is peak value, that divided by the peak value of the triangular signal, that is peak value of the carrier, or that's called VTRI. That ratio we call it as modulation index, MA, amplitude modulation index, MA. Another parameter is the MF, that is frequency modulation index. That is the ratio of the switching frequency, that is here, this is the switching frequency, that divided by the modulating signal frequency, that this one is the modulating signal frequency. That ratio we call it as frequency modulation index, MF. Therefore, these are two terms to be is to be explained, or that will be the application will be later in the coming slides. Therefore, in this inverter output voltage, that is VA0, this pulse width will be changing as shown this one between plus VD by 2 and minus VD by 2, and the fundamental of that voltage will be in phase to the modulating signal or reference signal. Now continuing the harmonics of the inverter output voltage, single phase half bridge inverter, sine wave PWM. As we have seen, this is the inverter output voltage, and we can see that one the pulse width is changing sinusoidally, that it is pulse width is increasing maximum. It will be maximum, that will be reducing again in the pulse width in the negative direction, the pulse width is here, and then this is the output of the inverter, and the fundamental voltage is this one, and this is this is a plus VD by 2 and this is minus VD by 2. And here, as we have seen in the two ratio, but we call it amplitude modulation ratio or index, MA equal to the maximum magnitude of the control voltage or modulating signal voltage divided by the maximum value of the triangular signal. That ratio call it as modulation index, amplitude modulation index, and the maximum magnitude of the fundamental is given by this modulation index divided into VD by 2. This is equal to plus VD by 2, then it's equal to minus VD by 2. Therefore, into VD by 2, that is, this is the maximum magnitude of the fundamental. This maximum magnitude of fundamental is given by MA into VD by 2. Therefore, by changing the modulation index, we can change the maximum magnitude of the fundamental, or thereby you can change the RMS value of the fundamental. And coming to the MF, that is frequency modulation index, the switching frequency, assume that switching frequency equal to 750 Hz, triangular switching frequency equal to 750 Hz, and the reference or modulating signal frequency equal to 50 Hz. Then frequency modulation, as per that definition, it is the switching frequency 750 divided by modulating signal frequency 50, which is equal to 15. For MF is equal to 15 as an example, MF equal to 15, and here this is shown the harmonic spectrum. Harmonic spectrum means what are the different frequency components in the output of this inverter voltage. What are the different, if you do the Fourier analysis, we'll be getting what are the different frequency components. That is plotted, that is called the harmonic spectrum. In that case, VA1 equal to MA into VD by 2, or this is a fundamental one, or here this axis is plotted against, that is the maximum, the VAH or harmonic, any harmonic, divided by VD by 2. So that is plotted against the harmonic number as such here, and we can see that one, this is the fundamental one corresponding to the fundamental signal, that is 1 represent the fundamental one. Then corresponding magnitude, if you divide this one, we'll be getting MA. For example, in this case, we are taking the MA as 0.8, modulation amplitude modulation index as 0.8. Therefore, it is equal to 0.8. Therefore, this is a fundamental one, and all other harmonics are centered at MF, 2MF, 3MF. Or MF means frequency modulation index. In this case, it is taken as 15, or MF is equal to switching frequency divided by modulating frequency. Therefore, near to MF, that band, this is the harmonics, near to 2MF, both sides, near to 3MF, like that one. Or we can say that harmonics are pushed to at a high frequency, centered at MF, 2MF, 3MF. Therefore, that is the advantage of sine PWM. The harmonics are centered at high frequency, that can easily be removed by low value of inductance or low value of LC filters. The size of the inductor required for filtering this one will be less. Unlike square wave inverter. In square wave inverter, the low frequency components are there. Therefore, like third harmonics, fifth harmonics, seventh harmonics, etc. will be there. In that case, square wave inverter, there you need a large value of inductance, or the size of the inductor will be more. But that is the one advantage of Sine PWM. The size of the inductor is reduced because harmonics are centered at high frequency, that can easily be removed. And another advantage is that by changing the modulation index MA, we can vary the fundamental output voltage, or we can vary the RMS value of the output voltage. That is not possible in the case of square wave inverter. In square wave inverter, to change the output voltage fundamental, you have to change the DC bus voltage. But in this case, by changing the modulation index MA, you can change the maximum value of the fundamental, or you can say the RMS value of the fundamental can be changed. So these are the two advantages of Sine PWM. Continuing the harmonics of the inverter output voltage, single phase half bridge inverter, already we have seen this is the harmonic spectrum, and the fundamental, all these are the harmonics centered at MF, 2MF, 3MF, where MF is called the frequency modulation index, and the harmonics in the inverter output voltage appear as a sideband centered at around MF, 2MF, 3MF, this one, that is where MF is the frequency modulation index. And here this is the fundamental output voltage, as I already explained, and the maximum value of the fundamental output voltage is given by MA into VDC by 2, where this is equal to VDC plus VDC by 2, this is equal to minus VDC by 2. Therefore, by changing the modulation index, we can vary the maximum value of the fundamental voltage. Now let us PWM pulse width modulation with bipolar switching, single phase full bridge circuit. Previously we considered single phase half bridge circuit. Here this is a full bridge circuit, and in that there are two legs. In each leg there are two switches. It is marked as TA plus, TA minus, TB plus and TB minus. And here the control low is that the total voltage VD is divided into equal value plus VD by 2 and minus VD by 2. The control low is that, again, this is the modulating or control voltage or reference voltage. All it is called that one. Therefore, here it is known as this a control voltage. That control voltage or modulating voltage is compared with a high frequency triangular voltage. So that's a carrier signal. Therefore, this is a modulating signal or reference signal or control signal that is compared with a high frequency carrier signal or triangular signal. And the control low is that one. If this control voltage or control voltage magnitude is more than VTRI, that is, for example, more than during this period, more than VTRI, TA plus and TB minus are, that is TA plus and TB minus are switched on. Then we will be getting here, it is equal to, that's connected to this plus VD, and here it will connect to minus VD. Then we will be getting this voltage equal to plus VD. VA0 minus VB0 is equal to plus VD. The second one is that if that is, we'll be getting plus VD here, plus VD. Again, when being control voltage, that this voltage or modulating signal voltage is less than the carrier voltage, then TB, that is, will be here TB plus and TA minus. TB plus and TB minus are on. Therefore, here in that case, negative voltage comes here and here positive voltage comes here. Here the voltage will become, the voltage between this A and B, that will become minus VD. VA0 minus VB0 equal minus VD. For he'll be getting minus VD. Therefore, depending upon the magnitude of this reference or modulating signal and the carrier or triangular signal, the output voltage of A and B, that will be either plus VD or minus VD. That will be also, or you can say that one. Again, the pulse width of this one is changing. For example, here plus voltage magnitude is increasing and that is reaching, and it's reaching to maximum value. Again, the plus voltage magnitude is reducing, and then it is again negative magnitude voltage is increasing, again negative magnitude is reducing. Or you can say that one, if you integrate this voltage, you'll be getting the fundamental one. Or this is the, if you do the Fourier analysis, this is the fundamental voltage which is in phase to the modulating signal or the reference signal or the control signal. We call both are all are same. Therefore, here this is the output voltage between A and B obeying this control law. Therefore, this is the modulating signal or reference signal that is compared with a high frequency triangular signal, and this is the output voltage of the inverter A and between A and B. It will be either plus VD or minus VD. That is why it is called bipolar switching. Either the output voltage will be plus VD or minus VD. And the maximum value of the fundamental voltage, as we have seen in this case, it is equal to MA into VD. Unlike the previous case MA into VD by 2, because it was oscillating from plus VD by 2 minus VD by 2. But in this full wave bridge circuit, it is oscillating from plus VD and minus VD. Therefore, the maximum value of the fundamental is given by MA into VD. And in bipolar switching scheme, the output voltage have both polarities, that is both positive and negative polarities during the switching. That is why it is called bipolar switching. And this is the control law, and this is the output voltage between A and B. And this is the fundamental output voltage which is in phase to the modulating signal. And the maximum magnitude of that one is given by MA into VD. Therefore, we are getting a variable magnitude of the voltage by changing the modulation index MA. Therefore, normally the magnitude of the triangular signal will be kept constant. Only we are changing the magnitude of the modulating or reference or control signal. Therefore, by changing that one, you can vary the MA so that the maximum magnitude of the output voltage, fundamental voltage, can be changed. Another thing is that to change the frequency of the fundamental, you have to change the frequency of the modulating or reference signal. Therefore, in order to get a variable voltage, variable frequency application of this inverter, in order to change the maximum value of the fundamental voltage, we have to change MA, modulation index, or we have to change the magnitude of the reference signal. And in order to change the frequency of the output voltage, fundamental output voltage, you have to change the frequency of the modulating signal or reference signal, because our fundamental output voltage is in phase to the modulating signal. Thereby, you can get a variable voltage, variable frequency output from this inverter. Let us see the frequency response, or frequency rather than frequency response, it is actually harmonic response, harmonic spectrum as such. It's a harmonic spectrum as such. Therefore, it is a harmonic spectrum in case of a bipolar switching Sine PWM for a full bridge circuit. And we have seen this is the output voltage of the inverter, either it will be plus VD or minus VD, and we can see that pulse width is changing. The pulse width is changing proportional to the magnitude of the sine wave. For it is increasing and then again reducing, and increasing in the negative side, it is increasing, again reducing. Therefore, this is the pulse width is changing. That is why it's called pulse width modulation. But width is proportional to the magnitude of the sine. That is why Sine PWM. Therefore, in this case, if you do the Fourier analysis of the output voltage, it contains fundamental plus harmonics. And the fundamental is this one. This is the fundamental which is in phase to the modulating signal or reference signal. Therefore, that magnitude is, as we already seen, it is equal to MA into VD. Amplitude modulation index into the DC voltage. That is this one. That is the maximum magnitude of this one. Now, by changing the MA value, MA value means modulation, amplitude modulation index can be changed. By changing the modulation index, we can change the maximum fundamental voltage of the output of the inverter. And here, of course, the frequency is same as the frequency of the modulating signal. Now, if you see the frequency spectrum as such, harmonic spectrum, what are the different other harmonics? Apart from the fundamental, this is the fundamental one. Apart from the fundamental, there are certain harmonics that is shown in the harmonic spectrum as such. Therefore, these harmonics are centered at MF. MF means frequency modulation index. As an example here, if you are selecting a switching frequency of 750 Hz and modulating reference signal 50 Hz, the frequency modulation index is my 750 divided by 50, 15. Therefore, MF is equal to 15. Therefore, the frequency, harmonic frequency are centered at MF, or in this case 15, MF, 2MF, 3MF, like that one. These are the harmonics. Therefore, since the harmonics are centered at high frequency, that can easily be removed by low value of the inductance. So, the size of the inductor required for the filter to remove these harmonics are less. That is the advantage of Sine PWM. Therefore, what we want is only the fundamental. We want to get only fundamental. You want to remove all the harmonics. That can be removed by low value of the inductance. That is because harmonics are centered at high frequency, which can easily be, which is the multiple at the centered at MF, 2MF, 3MF, like that one. The last slide we have seen the bipolar switching, but in this one it's called a unipolar switching. In unipolar switching, the circuit topology is there's no difference. Same thing here. Two switches in each leg. There are two legs. This is TA plus, TA minus, TB plus, TB minus, DA plus, the feedback diodes, DA plus, okay, here DA plus, DB plus, DA minus and DB minus, and this is the total voltage, DC bus voltage VD. And circuit topology is same, but the control method is different. In this case, the two or modulating signals or reference signals are using. One we call it as V control. This is called the V control. And the second one we call it as minus V control. It's a 180 degree out of phase with the V control. There are two control signals are using, and the reference the carrier signal is same carrier signal, but two reference signals or control signals are using. They are 180 degree out of phase. And the control load to for this controlling the switches, if V control is more than VTRI, that is, this is a V control. This one is V control. If V control is more than VTRI, then here TA plus is on. TA plus is on. When TA plus is on, here VAN, this voltage of this one with respect to this one. VAN is equal to, he'll be getting, it is equal to VD, because this is with respect to N, this voltage is equal to VD plus VD. The second one is that if V control is less than the triangular voltage here, during that period, here the rule TA minus is on. When TA minus is on here, this point is connected to this one, or therefore VAN will become 0. Therefore here VAN equal to 0. Therefore this is the plot of VAN obeying this control law, the top one, VAN. And same minus V control, that is this one, that is compared with the triangular one, that is to control the second leg. Therefore minus V control is more than VTRI, TB plus is on. As TB plus is on, here the voltage is equal to plus VD. And similarly, when minus V control is less than VTRI, then TB minus is on. When TB minus is on, here this voltage is equal to 0. Therefore, this is the control law in which there are two control signals, plus V control and minus V control, and that is compared with the same triangular signal, and obeying this control law, we'll be getting, this is the voltage of this leg with respect to neutral, and this is the voltage, second one is the voltage of this leg with respect to the neutral. For the net voltage VAB can be calculated VAN minus VBN, or this one minus this one, then you will be getting this voltage. For this is the output voltage VAB, that is called a unipolar switching. Why? Because always the voltage is changing only one direction. Here this is not, unlike the bipolar, the voltage is either it is plus, here plus VD you will be getting again 0, plus VD 0, like that. During the positive half cycle plus VD, and during the negative half cycle minus VD and 0. It will be oscillating minus VD and 0. Of course, the pulse width is changing proportional to the sign magnitude. Therefore, this is the unipolar switched inverter output voltage, and the fundamental is same. This is the fundamental same, and the same equation as we can use, that is equal to MA into VD. That is the fundamental magnitude of output voltage equal to MA into VD. Now continuing the PWM with the unipolar switching, as we have seen, this is a circuit topology, same as the previously discussed one, and this is the control plus control or control, and this is equal to minus control, that is compared with the same triangular signal as per the control law. If you operate this TA plus and TB plus, TA minus and TB minus, in that case this is the voltage of the leg A with respect to neutral, and this is the voltage of leg this point B with respect to the neutral. And if you subtract VAN, this is called VAN, and this is equal to VBN. VAN minus VBN will be getting this output voltage, which is the voltage between VAB. For that is this one, and we can see that one it's a unipolar, only one polarity. In maximum output voltage, that is maximum output voltage of the fundamental is given by this one, which is equal to MA into VD, where MA is called the modulation index, amplitude modulation index, which is actually the ratio of the maximum magnitude of the control voltage or modulating voltage divided by the maximum magnitude of the triangular signal. Therefore, normally, as I told you, triangular magnitude won't be disturbed. We'll be changing the magnitude of the modulating or reference signal. By changing that one, you can change the MA so that the maximum magnitude of the fundamental can be changed. And the frequency of this output frequency is same as the frequency of the modulating signal. Therefore, in order to change the frequency, we have to change the frequency of this reference or modulating signal. Therefore, the unipolar PWM inverters are better in terms of efficiency and lower THD, and as compared to the bipolar inverter. We'll be seeing the harmonic spectrum in the next slide. Now let us compare the harmonics in the inverter output voltage, the unipolar as well as bipolar switching scheme. And this is the bipolar switching scheme output voltage. It will be oscillating from plus VD and minus VD. Of course, the pulse width is changing proportional to the sign magnitude. And this is the fundamental output voltage. Fundamental output voltage. And if you do the Fourier analysis, the harmonic spectrum, the different frequency component is plotted. This is the fundamental one corresponding to MA equal to say here 0.8 and MF equal to 15. This is equal to the 0.8, which is equal to the fundamental one, and these are the harmonics centered at MF, 2MF, 3MF, like that. That's the frequency modulation index. For the harmonics are centered at high frequency, that can easily be removed. This is the case in bipolar switching. But same thing if you go to the unipolar case, this is a unipolar output. It will be plus VD or 0, like that during the positive cycle, and during the negative cycle minus VD or 0. And of course the pulse width is again changing proportional to the magnitude of the sinusoidal. And this is the fundamental one. Again, the magnitude of the fundamental, same equation, MA into VD. That is the, of course, RMS value equal to MA into VD divided by root 2. For this is the, voltage spec, picture as such, or diagram of the inverter voltage and fundamental. And if you looking to the frequency spectrum of the unipolar one, you can see that one. This is a fundamental, and here the MF nearby nothing is there, or near to 2MF, 3MF, like that. Or if you compare this harmonic spectrum of the harmonic spectrum of this bipolar switching and unipolar switching, you can see that one harmonics are less in the case of unipolar switching. For bipolar switching has two levels at the output, either plus VDC or minus VDC. So THD performance is poor compared to the unipolar. It is poor, and however, due to the absence of zero state, there is no zero state in here. There is no chance for the flow of leakage current. Unipolar pulse width modulation has three levels. It will be plus VDC or 0 or equal to minus VD. Therefore, three levels are there. Of course, levels, but here we can say that when harmonics are less compared to the bipolar switching. Looking into the harmonic spectrum, it is very clear. THD is less in the case of unipolar. THD of the the inverter output voltage is relatively less compared to the bipolar switching. Magnitude is given by, in both cases, it is equal to MA into VD. VD is that DC bus voltage or DC source voltage, and this is oscillating between plus VD and minus VD, and this will be plus VD 0 or minus VD 0, like that one. Now let us see a three-phase inverter using Sine PWM. Previously we have seen a single-phase inverter. Now three-phase inverter. This is a circuit topology as three-phase. There are three legs. In each leg there are two switches. It is marked like this one: TA plus, TA minus, TB plus, TB minus, TC plus and TC minus. Across the each switch, controlling switch, there are feedback diode DA plus, DB plus, DC plus, D here similarly DA minus, DB minus, DC minus. These are feedback diodes, and these are the total VD DC voltage, and plus VD by 2 minus VD, that is divided using two same value of the capacitor. Therefore, this is a circuit topology, and this is the leg A is taken here, and this is the leg B is taken here, or this is the point C is taken here. This is the neutral point. Therefore, we are going to calculate what is VAN and what is VBN and what is VCN by using the Sine PWM. That's called inverter output voltage of each leg with respect to the neutral. Therefore, this is the three modulating signals are using. In the three-phase signal, these are modulating signal or reference signal or control signal. All are same. Therefore, here this is the phase A modulating signal, and this is the phase B modulating signal, and this is the phase C modulating signal. Or that modulating signal is compared with the same triangular signal. Now, the control law is this one. This is the control law. That is when the corresponding voltage. So, for example, VA, when VA is more than the triangular voltage. For example, here when VA is more than the triangular voltage, then TA plus is on. That is TA plus is on. And when VA is less than triangular voltage, that is during this period, therefore when TA plus is on means here this will be getting, you will be getting a, here plus VD will be getting, when the here, that is when this control voltage is less than this triangular voltage, in that case TA minus is on. So TA minus is on means this voltage is connected to the neutral point, or you'll be getting VAN will be that voltage is equal to 0 voltage. VAN will become 0. Therefore, this is the control load to control this leg. Similarly, to control the leg B here, this is the same role, same law is there. Again here, if VB is more than V that is this is a VB or this is a modulating signal. If that is more than the triangular signal, then corresponding TB plus is on. Then you will be getting the corresponding voltage VB. VB will be getting. And when it is less, or when this VB is less than this triangular signal voltage, then corresponding here the lower one TB minus is on, then here voltage will become connected to this is the neutral point. Therefore, you will be this voltage equal to neutral, or that voltage is become 0. You'll be getting 0 voltage. Therefore, this is the control law for the leg B. Similarly, leg C is the same as the control law. Applying this control law, we can get what is the voltage of this leg point A with respect to N. That is this one, VAN. So therefore, this is this voltage equal to VD, and this the plot is equal to VAN. Similarly, for this one, VBN, voltage of this one with respect to the neutral point. This is the neutral point, which is equal to this. This is a plot. Therefore, again, you can say pulse width is changing proportional to the magnitude of the sinusoidal signal. Therefore, this is a VAN and this is equal to VBN. Therefore, the net voltage VAB is given by the line voltage VAB is given by the phase voltage VAN minus the phase voltage VBN. Or this voltage is the phase voltage VAN, that minus VBN. That will be getting, this is the plot of the line voltage. For VAB is this one, VAB like that one. You can see if you are plotting the VCN, then VBN minus VCN will be VCB. Like that, we can get the line voltages. This is the plot of VAB. This is the plot of VAB in which the line voltage VAB, and the fundamental of that one. That fundamental of the voltage, mostly that will be in phase to the modulating signal of line voltage. This is because line voltage, if you take the VAB line voltage, this one VAN minus VBN is the line voltage of this reference signal. Therefore, in that case, this fundamental voltage will be in phase to that line voltage. That is why there's a shift is like this one. This will be in phase to the line voltage, reference line voltage. Therefore, the maximum magnitude of this one, again, we can calculate what is the maximum magnitude of the fundamental. Therefore, this is the output voltage between A and B, line voltage, and this is the fundamental voltage of a line voltage VAB. Therefore, this is the circuit topology, and this is the controlling method. Like three modulating signals are there 120-degree apart. This is phase A, phase B, and phase C, and that is compared with the same triangular signal. And obeying this control law, we are getting the corresponding the voltage VAN, VBN, and VCN. And to get the line voltages, VAN minus VBN will be VAB. Like that one, you can get the line voltages. Now, continuing the three-phase inverter using Sine PWM. Here, the circuit topology already explained that one. And this is the line voltage VAB. That is a VAB line voltage. That is, of course, the pulse width is changing proportional to the sine, and the fundamental one is shown here. This is the fundamental magnitude of that one. Now we have to calculate what is the fundamental line voltage. That is, let us see how it is being calculated. So for the maximum value of the fundamental line voltage, that is represented as maximum value of line to line voltage. That is maximum value of the line to line or fundamental. That is fundamental maximum line to voltage. That is equal to root 3 times maximum value of the phase voltage. Root 3 times maximum value of the fundamental phase voltage. Root 3 times maximum value of the fundamental phase voltage is the maximum magnitude of the line to line voltage, fundamental line to line voltage. Therefore, again coming to here, RMS value of this one, it's the maximum magnitude. RMS value of this one is equal to maximum magnitude of this one divided by root 2. For root 3 into maximum magnitude of fundamental phase voltage, that divided by root 2. Therefore, if you substitute here, what is the maximum magnitude of the fundamental voltage? Maximum magnitude of the fundamental voltage already it is derived as in the case of MA into VD divided by, in this case, MA into VD divided by 2. It is MA into VD by 2. That is here, and that divided by root 2, or we will be getting it is equal to 0.61 MA into VD. 0.61 MA into VD. The maximum magnitude of the phase voltage VAN maximum magnitude is given by MA into VD divided by 2. Why it is VD divided by 2 means that if you see the spectrum, or if you see the voltage waveform here, we can see that one, it is changing it is changing from 0 to V only, 0 to VD only. But in the bipolar case, we are seeing it is equal to plus VD by 2 minus VD by 2. The total change is equal to VD is there. 2 VD is there. That is why that equation MA into VD comes. But here the total change equal to 0 to VD here. And if you calculate the fundamental one, if you calculate the fundamental one, it is equal to MA into VD divided by 2. That is this one into root 3 divided by 2, or it equal to 0.612 MA into VD. Therefore, this is the maximum value of the line voltage of the three-phase maximum value three-phase. Inverter using sine PWM. Maximum value of the line voltage is given by 0.612 MA into VD. Therefore, by changing the MA modulation index, you can change the line voltages. And the corresponding harmonic spectrum is also shown here. Or high frequency is the fundamental, and all the harmonics are centered at high frequency that can easily be removed. Therefore, that is the advantage of sine PWM. Therefore, if you are using a sine PWM, we can change the one advantage is that harmonics are centered at high frequency that can easily be removed by a low value of the inductance, so the size of the filter is reduced. Second advantage is that you can change the output voltage magnitude as well as frequency. You can change the fundamental output voltage magnitude by changing the modulation index, and you can change the frequency mean by changing the frequency of the modulating or reference or control signal. Therefore, thereby you can get a variable voltage, variable frequency output with a low harmonics. So that is the advantage of three-phase inverter using sine PWM.